In this video, I will be discussing a perfect square proof. Proof that for all positive integers n to the power of 4 plus 2n cubed plus 2n squared plus 2n plus 1 is not a perfect square. First of all, I'm going to make this long expression n because it's going to be easier to write in the proof. So let n to the fourth power plus 2n cubed plus 2n squared plus 2n plus 1 equal to n. And we actually have two methods to solve this problem. I'm going to use the first one as factorization, the second one is using the properties of perfect square. So for the first one, factorization, well, we can split 2n squared n to the fourth power plus 2n cubed plus n squared. This is a very common perfect square formula. Plus n squared plus 2n plus 1. This will equal to n squared plus n squared plus n plus 1 squared. You have to know that the perfect square formula, which is like x plus y in parentheses squared equals to x squared plus 2xy plus y squared. And you have to split 2n squared to form the sum of two perfect squares. Then you can factor out n from the first perfect square. Yeah, n plus 1 squared plus n plus 1 squared. And factor out n plus 1 squared now, and we're basically done. N squared plus 1. So like since n plus 1 squared is perfect square, while n squared plus 1 is not perfect square. Well, a perfect square times a not perfect square is not perfect square. So this means that n is not perfect square. And that's the first way, factorization. Now the second way, you begin in the same way, which is note that n to the fourth power plus 2n cubed plus n squared equals to n squared plus n parentheses squared. And we have 5 terms in n. And we want a perfect square, so the reasonable thing to do will be add another term to m squared plus n. So n squared plus n plus 1. We added 1 here instead of like any normal term because we have a 1 here. And to have this 1, we need a 1 in the perfect square. And we know that 1 squared is 1. So after expanding this, well, here we will use the perfect square formula for 3 terms, which is right here, a plus b plus c squared equals to a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc. So this will equal to n to the fourth power plus n squared plus 1 plus 2n cubed plus 2n squared plus 2n. This will equal to n to the fourth power plus 2n cubed plus 3n squared plus 2n plus 1. So through direct operation, we can get that n squared plus n squared, this will be less than m less than n squared plus n plus 1 squared. And here, we can actually use identity of perfect square. Like, if n squared plus n and n squared plus n plus 1 squared are consecutive perfect squares, there exists no perfect squares between them. But I'm going to prove this for you. So, we'll do a proof by contradiction. Assume that when m equal to x squared, we're assuming that m is a perfect square. And now, since n is a positive integer, we can directly take away the square sign. Like square root of square. It's positive integer, so after directly taking away the square sign, you get n squared plus n less than x less than n squared plus n plus 1. And since n squared plus n and n squared plus n plus 1 are consecutive integer, so there does not exist integer x. So m is not perfect square. As you see here, if x does not exist, then this means that m cannot be a perfect square. So that is how you solve this problem using two ways. The first way is factorization, and the second way is using the properties of perfect square and proof by contradiction. Thank you for watching.